Hi. Today we're going to bring our model of the atom up to speed with the modern day. As a way to get started, take a look at these problems. These are from previous lessons. Hit the pause button if you need to. There's a link to your reference tables above my head. But I'm going to get started. To write an excited configuration for aluminum, we should first look up the ground state configuration of aluminum, which is 283. So what we're looking for is something that has 13 electrons and isn't 283. So that rules out C as a potential answer, and also B and D because that's the wrong total number of electrons, leaving us with A. For the second problem, as an electron moves from ground state to excited state, the electron increases in energy. That's how that transition happens. That's kind of a definition thing. So for today, really, I want to talk about the Bohr model and its shortcomings. Turns out that the Bohr model is an excellent description for the hydrogen atom. Here's your 3 to 2 transition, your 4 to 2 transition, your 5 to 2 transition, and your 6 to 2 transition. And it's super clear that these individual transitions release a discrete amount of energy, a thin quantized energy. And then when you start looking at things like neon and iron, there's way too many lines. There are too many lines for a Bohr model to be good at really explaining what we're seeing. And these multi-electron systems can't be explained by the Bohr model of these discrete energy levels. So we have to say something more. Really what ends up happening is that electrons have this interaction with each other that impacts more than just repulsion and attraction. So to help explain this, I have a Dr. Quantum here who's going to explain a couple things to all of us. And let's get started. Take any notes.
So, what they taught us in school isn't really the way it is. And that our senses are playing tricks on us. You just gotta wonder, what is this reality that we find ourselves in? Quantum physics says it's all just waves of information. Do I believe that? I hope so. Yikes! And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter, through. but we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly.
Mostly because of that measuring device.
But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands.
Oh, I remember now. Yeah, that has to do with superposition and, Heisenberg's uncertainty. That we don't need to talk about, so I am going to leave it there. So just to recap what was said and give a little bit more information, what we have here is an image of something we know that happens in the macroscopic world with waves. Waves being a way of energy propagating through space. On the bottom, what we have is you're dropping two balls into water and they're making a bunch of waves as they bounce in the water. And you can see that the waves created from the two balls interact with each other in the way that we're seeing in this animated GIF. The top one is stationary, the bottom one is not. And when the top of one aligns with the bottom of another, the overall resulting wave is flat. And you can see here these bands of no wave in between bands of very high wave. And you can see where the peak interacts with the peak, you get a doubly tall wave right here. And so when you have more than one wave, you do get this interference pattern of peaks and troughs, of maxima, minima, zeros, and twos, essentially. Turns out that that's what waves do, so light would do that too. If you've ever played around with diffracting light through a prism, that's kind of how that works. But it also turns out that that's how particles work, as in subatomic particles, like electrons. When you get towards really small particles, the behavior between particle and wave, the differences start to blur. And it even ends up becoming a factor of whether or not you are observing it that changes how it behaves. And to really wrap our minds around this, the idea that an electron can go through two holes at the same time would really get at this idea of location being uncertain. So if you have a propeller that's not moving, I know that the propeller is, a certain width and it exists in this place in space. If the propeller was moving, though, I don't know where it is. So I could maybe take a picture of it, but when I take a picture, it's a blurry picture because as I take the picture, the propeller is moving through a certain amount of space. The propeller still has its width. Its width was only about that big. But the actual location now is unknown to me. All I know is that it exists somewhere in a certain range, but its exact position is uncertain. So to put these two thoughts together, the idea that electrons will exist as particles because we see, they get lost and gained in and out of atoms. They actually also exist as waves because when you try and measure them as waves, they end up proving that they're behaving that way. So a number of scientists had this data that said electrons were behaving like waves. But the nice thing about waves is that if something has a wave-like property, if there's some sort of fluctuation in energy or over space or similar, those waves can be described with a mathematical formula. And the mathematical formula, so like this is an example of like a sine curve where the value of y is equal to the sine of whatever x is, so the x and y positions are related. You can write an equation that relates the energy of an electron to its location in the nucleus. Now it turns out that the information, the formula is a lot more complex, but what you can do is maybe we can pick out little pieces. This psi character is the wave function, the function that describes the properties of the wave that is the electron. And we have here x, which is a position, and then we have here u, which is energy. So all three are related. The function that describes how the wave behaves, the electron's energy, and its position are all related in this equation. I don't really want to go through the derivation. I don't need to go through the solution because it's been a while and I don't want to make any mistakes. But what I can tell you, rest assured, is that when you get those answers, you get things like this. The wave mechanical model put down by Schrodinger says that, and others of course, says that electrons exist in orbitals, which is not really a location, it's more of a probable location. The electron is loosely associated with being found anywhere in the region shown, the electron cloud. If you were to take a picture of the electron, you are interacting with the electron, you're probably like shining a light on it to take the picture. The electron then collapses like we saw in the video, and then it ceases to behave like a wave and starts behaving like a particle again. But as long as no one is trying to shine lights on it, we do have data, if depending on how you look at these electrons, to say that they behave like particles and like waves. Now, in terms of the wave portion, if you can solve any of this, if you plug in the energies that we saw from the Bohr model, because those energies, those lines on the spectrum, still correspond to energies of light, you can find positions. And this is only in the x direction. You'd have to do x, y, and z. But I wanted to take some time to just show you. This is another form of the wave function. But what we have here in these images is low and high probability of finding the electron in those locations. So what we see is a number of shapes. I see shapes that are round. I see shapes that look like they have two lobes. And then I see shapes that look like they have 4 or even 6 lobes. And each of those answers to the wave function are different orbitals. Now you can see there is we have 2 and 3 as our first numbers. So I want to actually pick apart what these numbers stand for to maybe put a little bit more information into what this all means for everyone. So as we saw with the Bohr model, the atom has several principal energy levels. These are the shells that we were talking about, and they're numbered N, 1, 2, 3, 4, 5. Each principal energy level from here on out is going to be divided into one or more sublevels. We're going to represent that with the letter L. These are called quantum numbers. I'm not going to spend a lot of time on them, but I'm telling you what they are. And then each sublevel can be divided into one or more orbitals. So each image you see on this picture here, 10, 4, 7, 19 pictures, each of these is an orbital, one potential location for an electron based on the Schrodinger equation for a given atom. These are the orbitals for hydrogen. They are grouped into sublevels and principal energy levels, but these are individual answers. To make things a little bit cleaner for you, I got some 3D models. These are the individual orbitals, but they are grouped into sublevels. So this is what we would call the S sublevel, and it has 1 orbital. This is the P sublevel, and it has 3 orbitals. You can see each of these is a different potential location of the electron, and this is the D sublevel, and there are 5 orbitals. I'm going to go through all of this in a later video, but I wanted to give you a little bit of exposure as to the idea of principal energy levels are broken up into sublevels, are broken up into orbitals, and from all of this we get these individual orbitals, their individual locations of electrons. And I think at this point it might be worth saying this is why sometimes we kind of stay at the Bohr model. Because even though the Bohr model only really describes hydrogen correctly, these multi-electron systems being far more complex, it's good enough for most of what we do. And this is a point in chemistry where we start saying, well, I mean, we could put more layers and this is technically the correct answer, but really at the end of the day, we can pick the model that best lets us get through what we need to get through. These orbitals might come in a later course, but really in terms of bonding or interactions of like ions and covalent stuff and molecules. The Bohr model actually does a sufficient job. We'll use this information once we build it up to give a little bit of a clearer picture to some things that don't necessarily fit what we expect. But mostly this is a jumping off point to complex stuff that will only apply some of the time. Thanks for watching.